what you did in the dark. So light 'em up, light 'em up, light 'em up, I'm on fire. So light 'em up, light 'em up, light 'em up, I'm on fire.
Yes, indeed, we are on fire as we move into assignment number 2 for the summer. And I tell you what, I'm going through some massive calculus withdrawal here this summer, and my heart wants to turn this into a 13-hour video. I'm just kind of chomping at the bit to talk about some calculus, but I'm going to do my best to resist that urge and keep it as short as I can. But there are a lot of things that we want to go over tonight. There's a lot of things I want to try to emphasize and get us ready for September when that rolls around. But anyway, tonight we're going to talk about, the first half of the video is going to be on the difference quotient and its very close cousin, the definition of the derivative. And the last couple of years we've kind of assumed that these two things are the same, and they're not quite the same. There is a subtle difference that I want to emphasize tonight. And then the second half of the video we'll talk about L'Hopital's rule, and we'll find out why that's going to be one of our best friends throughout the year. But before we do so, and I want you to hang in there in these first couple minutes, the difference quotient and then the definition of the derivative, they're not going to mean anything to you unless you understand this very simple concept. And if you have your pre-calc notebook handy, or if you've already gotten your calc notebook, then this would be a great thing to put in there for day one. What we've got here is we've got our axes. We're going to zoom in on the first quadrant, and we've got some peculiar function that behaves like this. So we'll just call him, we'll just name this f of x perhaps. Now, let's see. Let's pick a random point here, and we'll call it A. And then we have that point on the curve that corresponds to that moment. And the y-coordinate over here is f of A. And so that ordered pair is really A comma f of A. Not the most exciting ordered pair you've ever seen, but it's a fun one. Now what I want you to imagine is you start at the origin and you walk to the right A units, and then you walked an additional H units, and that put us about right here. So that new point is A units plus H units. We'll find that corresponding point on the curve. His y value is f of A plus H. So as a whole ordered pair, that would be A plus H for the x-coordinate and f of A plus H for the y-coordinate. Now what we really want to get at here is we want to talk about the slope between those 2 points, and you're going to laugh at my line here, but I'm going to try to, almost, not too bad. But anyway, that's what we call a secant line, and the slope of that secant line measures the average rate of change for a function f, okay? And that hopefully is just, major review. So what is the average rate of change of the curve represented by f of x between those 2 points we've found? So let's see, the average rate of change, and I'm going to just abbreviate this, AROC, average rate of change, would be, let's see, I need my y-coordinate subtracted by my other y-coordinate, and then my first x-coordinate minus my second x-coordinate. And then as we clean that up, you'll notice the a's on the bottom cancel, and we get just h. Now this is what I call my difference quotient, dq. All right. Now what's going to happen though, as mathematicians, we weren't satisfied with just the slope of a secant line. What we wanted to do was we wanted to get our hands on this blue point up here, and we wanted to drag that point ever closer to the original point until it landed right on top of the first point, okay? So the first point is stationary. We're going to grab the second point, and we're going to drag him closer and closer and closer to this point right here until the 2 points laid perfectly on top of each other. And then at that moment, we've gone from a secant line into a tangent line, a line that just kind of skims the original curve. And so we wanted to know what's the instantaneous slope at that particular moment. And we said, well, basically what happens is, in order to find the slope at that moment, we want to take what we already built, but what we want to do is we want the value of h to get infinitely small, so small that it approaches 0. So it is the difference quotient we had just moments ago all over h, okay? And now what we have in blue here is what I call the definition of a derivative. What's the difference between a difference quotient and the definition of a derivative? Well, the difference quotient is the slope of a secant line, aka average rate of change. And the definition of a derivative now has the limit in front of it here, and we're now finding the slope of a tangent line, aka instantaneous rate of change. So just a real quick summary of what we just found. We said that the difference quotient is going to be, now a lot of times what's going to happen is the A's that I used on the previous slide, they're going to become X's a lot of time on your paper. And so the slope between those two stationary points is your difference quotient. And just keep telling yourself, that's a secant line, or it's measuring the slope of a secant line. And what you're actually doing is you're measuring the average rate of change of a function. Okay, that's all what we would call, very primitive math here. Now we upped the ante a little bit, and we said the definition of a derivative is what happens when h approaches 0, and we've got everything else here. And what you're doing now is you're calculating the slope of a tangent line, and it's no longer the average rate of change over a given interval. What you're now finding is what we call the instantaneous slope, or instantaneous rate of change. So those are the key features we want to differentiate between. Now perhaps you spent a lot of time on the difference quotient and the definition of a derivative in pre-calc, and they're very long, tedious questions. And so here's the catch. We're already going to start talking about the AP exam right now. See, the AP exam loves this concept, but they don't want to waste your time. They don't want to waste 15 minutes on this simple concept. So I'm going to talk about in this video how the AP is going to test you on your understanding and your appreciation for this particular concept. So as a warm-up here, what I want you to do is I want you to consider the function f of x equals sine of x. And what I want you to do is I want you to find his derivative the long way. So we would take that definition and we'd say, well, it's the limit as h approaches 0, and I'm going to substitute the quantity x plus h in for x, and then I'm going to subtract the original function, and then I'm going to divide by h. So that's how I would set it up. Now, perhaps you saw a problem like this earlier this year, and this would be like, this problem would take you, it would take me at least 15 minutes. I would have to use a very fancy sum of two angles formula right here. There's some very complicated math in the process of cleaning that up. So fortunately, we're going to skip that. But what that is if we did clean that up, what you're finding is the derivative. And what does the derivative do? The derivative measures the slope of that function at any given particular moment. Now, what if you wanted to find the slope of a tangent line, say at a specific moment, like x equals pi over 2? What you would do is you would take the derivative you already have on your paper, and you would substitute the value pi over 2 in for those x's. And actually, the sine of pi over 2 is just a 1, and so I cleaned it up, simplified it a little bit. And this expression that I have right here represents not only the derivative, but the derivative evaluated at a specific moment in time. And if I had the ability to clean this up right now, I would know the instantaneous slope right at x equals pi over 2. Okay, so finally we're going to talk about an AP question, and basically they're going to throw something really ugly at you like what we have on the screen already, and the magic words and the directions, they're going to say, hey, just evaluate. That's all they're going to say. It's going to sound so innocent, and yet it's going to look so ugly. So here's what we've got. We've got this very ugly limit. Now what I want you to zoom in on is the fact that we're using h's. This is kind of a dead giveaway on the AP exam, that when they use h's, they're testing you on the concept of the difference quotient. So what's happening here is they're taking a function and they're trying to find the derivative of it. There's a really long way to do this problem, and then there's a really, really short way. And I'm going to focus on the short way, of course, because we want to be as efficient and as quick as humanly possible. Now, the question is, what function are they trying to derive? Okay, so on your paper, when you're doing your summer assignment, I want to see very crisp notation, like f of x equals blank. Okay, what is the function? Who are they applying the difference quotient or the definition of a derivative to? The key here is, if you simply cover up the h's and those first three terms, you will reveal the function. So if I cover up the h on the first expression here, pretend that h isn't there for right now, and you would see x cubed. And then if you covered up this h, you would see 2x squared. And if you covered up this h, you would see minus 5x. That, ladies and gentlemen, is the function that they are attempting to derive. Now you'll notice over here the signs are switched because there was, you know how there's that minus f of x in the difference quotient? They've already distributed the negative, and that's why you see the signs change. But however, just identifying the function isn't our end goal. Our goal is actually to take his derivative. And so I'm going to use a very simple power rule. The derivative of x cubed is simply 3x squared, and the derivative of 2x squared is 4x. And of course, the derivative of the last term is negative 5. If you're a little shaky on your derivative rules, just review your pre-calc notebook, but the key here is identify who f of x is and then take his derivative and you're in great shape. So again, here's a tidier example. It looks cleaner maybe than the last one. And again, the directions are simply going to say evaluate. And what we want to do is we see the h's, so it's kind of a giveaway that they're testing us on the difference quotient. And we want to identify what function they're attempting to take the derivative of. And again, if we cover up the h, we will reveal the function. And so the function is simply the tangent of x. And then we just want to calculate his derivative. And again, it's just memorizing a rule here. And the derivative of tangent is, yes, I heard you. I know you're screaming it at your screen and saying the derivative is secant squared. And that's it. That's our final answer right there. That's the derivative. If I evaluated this limit using long, tedious techniques, it would simply equal secant squared. That's it. Now, believe it or not, this is just almost exactly like the last one. Again, the directions simply say evaluate. You see the h's, so you know it's going to be a difference quotient. They're testing you on your knowledge and understanding of the difference quotient. But what's going on? The question is, why does it look so much cleaner? In other words, what's missing on this one compared to the last one? Well, what you'll notice is there are no x's in this particular problem. So what happened? Why are they missing? Well, the reason they're missing is because they substituted a 0 in for x. All right. In other words, what they're doing is they're not only taking the derivative, but then they're going one step further and they're evaluating the derivative at a specific moment in time. So my goal is it's a three-step process, and I'm looking for this clarity on your assignment when you turn it in. I want you to identify the function. I want you to calculate his derivative, okay, f prime of x. And then what I want you to do is, in this particular case, I want you to evaluate the derivative at 0. Now, it won't always be 0. They just happen to pick that value this time. You may be evaluating the derivative at pi or at 2 or at 1 or some other value. So here's what I'm going to say. I'm going to say the function here, if I cover up the h, I'm going to see that the tangent of x was sitting there. His derivative, of course, is secant squared. And if I evaluate that function at 0, let's see, the cosine of 0 is 1, his reciprocal is 1, and if I square it, I get 1. So guess what this number represents? That's the slope. The slope when x equals 0 is equal to 1. Beautiful. Okay, this marks the halfway point on the video. We're going to entirely switch concepts. Now, the concepts are quite unique and different from one another. What they have in common is they both use a limit, and that's why I grouped them together on this particular assignment. Other than that, they really don't have anything in common. In fact, L'Hopital's rule is a rule that we're going to use to evaluate about 90% of the limits we see in Calc BC. It really is going to be one of our favorite rules. And the good news is it's one of the easiest things we're going to do all year. And basically, here's what he says. If they give you a particular limit, they want to know what's the limit as x approaches a for the quotient of, say, let's not use g, I'm sorry. Let me grab the eraser. I should be using, not that I have to, but I like to use f of x in the numerator. It's no big deal. I don't know why I did that, but okay. So here's what's happening. We're saying as x gets closer to a, all we want to do is we want to evaluate those functions at a, but something bad is happening here. What you're getting here is 0 divided by 0. That's called the indeterminate form. I don't know if I can spell that. Indeterminate? Does that look right? I think that looks right. Anyway, that's the indeterminate form, and basically what it means is you're unable to determine the limit of this particular function just by doing direct substitution. So what's going to happen is we're going to rewrite the limit in terms of the derivatives, okay? We're not doing quotient rule. What we're doing is we're treating the numerator and the denominator as if they're separate functions. We're taking the derivative of the numerator just by itself, and then the derivative of the denominator by itself. And then what we're doing is now we're doing a direct substitution, and we're hoping that we don't get 0 over 0. As long as I don't get 0 over 0, I've got my answer. If I did get 0 over 0 again, then I'd simply take another derivative to both the top and the bottom and evaluate it then. So that's basically how it goes. Let's try a couple. Okay, so here's our first example regarding L'Hopital's rule. Now, how do you know they're not testing you on your difference quotient or your definition of a derivative? Well, the giveaway here is the fact that they're not using an h here in this spot. And that's how you know it's a non-difference quotient type of problem. What you'll notice, if we go ahead and substitute that 0 in right now, we get the sine of 0 divided by 0, which is really 0 over 0. Aha! That's indeterminate form. We're unable to determine the value of the limit right now. So basically none of that worked. And I'll tell you what, that's going to happen about 99.9% of the time. I cannot recall a single AP question where direct substitution actually worked. So what I'm going to do is I'm going to rewrite it in terms of a limit. And this is where a lot of students in the past have lost points on their summer assignment because they forget to include that limit part. And the derivative using a little bit of chain rule is 8 times the cosine of 8x. Don't forget that you are using chain rule right there. Let's put a little star so you can slowly get the rust off. What you have is you had an inner function of 8x and an outer function of sine, so you had to employ the chain rule. The derivative of the bottom was simply 6. Now if I substitute the 0 in there now, the cosine of 0 is 1. So I actually get 8 over 6. And you could reduce it to 4/3 if you want, but one of the things you'll learn in AP Calc is that reducing your fractions is not required at any time. So a final answer of 8/6 is good. Wow, look at this feisty problem. Very, very nasty limit question. What you'll notice, if we do a direct substitution right now, which we should test, although I kind of just told you in the last problem that it never works, you get the natural log of 1 on top, which is 0. And on the bottom, oh boy, you get e to the 0, which is 1, and 1 minus 1 is 0. So yes, indeed, you do get indeterminate, which doesn't work. So I'm going to use L'Hopital's. I'm going to rewrite it in terms of a limit. Okay, don't lose points there. The derivative of my numerator, okay, whenever you take the derivative of ln, and we might have to review a little bit here, we might have to go back to our notebook, but it's the derivative of u divided by u. When I say u, I'm referring to this inner function or that inner quantity. His derivative is -1, and of course, divide by that original quantity. So that's your numerator. When we get to the denominator, the derivative of this 1 is 0. And then e is always the original function itself times the derivative of the exponent, which in this case is 1/2 because it's the coefficient of the x. And so you could clean this up, certainly. Mine was looking fairly messy. And in fact, I'm going to go ahead and take the time to do that. So it's -1/2 e raised to the x divided by 2 minus 1. Okay, now I'm going to do a direct substitution. Oh my goodness, I would take points off. If you're going to rewrite it, if you're going to clean it up, I want you to include that limit right up until the moment you substitute the 2 for x, which I'm going to do now. As I substitute that 2, I get -1 over 1 all over -1/2 e to the 0 power. Let's see, we clean that up just a hair. What do we got, folks? We've got a -1 divided by a -1/2, which turns out to be +2. There's my final answer using L'Hopital's rule and some fancy derivatives and some excellent notation. So I hope you picked up a few things tonight. I hope you got some of the rust off from the summer. I feel like we gained a lot of ground and talked about a lot of really high-quality things. So continue to take time to enjoy your summer. Don't do too much math, just enough to stay sharp. And I'll see you in a couple of weeks for video number 3.